Hello. Hey, let's get started. Last slot of the day, I want everybody to be able to start drinking on time. So, which might be now. Anybody drinking yet? Yeah, congratulations. Hi, my name is Alex Stamos. You're in the Building Security from Scratch session. Thank you all of you who could not get into the Netflix session and saw me as the sloppy seconds. I appreciate it. We are going to be talking about, well, obviously the cloud. This whole conference has been a little bit like a drinking game, right? Every time you hear the word elastic or cloud, I'm going to try not to use cloud as much as possible and still talk about cloud security. But kind of our topics today, we're going to talk about what the current state of the conventional wisdom is for cloud security and why it's perhaps more conventional than wise. We're going to talk about what things do and do not work in the cloud. And then we're going to talk about what kind of benefits we get specifically from AWS. Obviously, it's an AWS conference. Most of these suggestions work on any platform, but we'll specifically talk about AWS and AWS technologies and how you can look at the reality of cloud security and what you get from AWS and what you can build on top of the basis they give you. So a little background of why I'm up here. I'm co-founder of a company called ISEC Partners. We have a bunch of clients in the audience. We're a boutique security consultancy. And we help people secure and design secure systems up front, and then we handle incident response. When the you-know-what hits the fan and bad things happen, we get the call and we go in and help them out. And a lot of that incident response has actually been on the cloud, both the cloud providers and to customers of the cloud. We've done some big ones. We were involved with the Aurora stuff, which was the Chinese government hacking 35 American companies. 5 of those were clients of ours, which is actually probably not a great statistic for us to advertise. But that meant we got to get really deep and to see how people who are associated with foreign governments are doing attacks these days. And we also do kind of a day-to-day incident response all the way down to literally plumbing supply companies hacking each other and crazy ex-spouses and stuff like that. So we have a lot of experience in what really happens. I'm going to talk a lot about how hacking really happens on the cloud and what kind of incidents we've seen. I'm also now the CTO of Artemis Internet. That's a side company, a sister company to ISEC Partners. We've applied for the Secure TLD, which is going to be kind of a private neighborhood of companies that care about security that set our own rules about compliance rules that people have to follow, what security technologies we're going to use. Obviously, we're going to be a big target. There's already lots of people making fun of us on Twitter. And so we need to build a not just very secure, but a very reliable and robust and extensible infrastructure in the next year or so. And we're going to do it on AWS. So who owns the conventional wisdom in the cloud? And probably the organization that is most associated with cloud security is the Cloud Security Alliance. Who here has ever been to a CSA meeting or is a member of the Cloud Security Alliance? Oh, not as many people as I thought. Okay, that's good, because then I'm not insulting a huge number of people. Like I said, the Cloud Security Alliance is keeper of conventional wisdom. I'm going to talk about ways, I'm going to criticize their output. Overall, I think the CSA is something that needs to exist. I'm glad it exists. They've done a great job in helping pull forward accounting firms and compliance regimes and people who are not very savvy about new technologies and helping those people accept the cloud. And I think that's their most important role, is to help the old guard accept that the new guard knows a little bit what they're talking about. But overall, I don't think if you're going to sit down and build a new infrastructure on AWS that you should go and download a PDF from them and use it as your rule book, and that's what we'll be talking about. The Cloud Security Alliance has 3 major kind of members. So there's the cloud providers themselves. Amazon is a member, but that's a very late addition. Amazon, I don't know exactly when they joined, but certainly when the CSA was starting to get big a couple years ago, Amazon and the other big cloud providers were missing. Instead, the real initial founders of this were the security vendors, people who have made money throughout the last quarter of the 20th century selling boxes and selling software to install on your fully managed operating systems on hardware you own, right? These are people who have built their reputations, their companies, how they hire people, and their entire product line around how we used to build software and systems in, say, 2002, 2003. And these were the people that really started and laid the groundwork for what the Cloud Security Alliance does. And then we have the real old guard, people whom are actively hurt by the cloud, including a company there in the bottom left corner with a CEO who said that cloud computing is a myth and doesn't exist and such. So it's great to see them, people who think cloud computing doesn't exist, join something called the Cloud Security Alliance. When you look at this list, you definitely see that there's not a huge amount of overlap for goals here, right? If you're the cloud providers, your real goal to something like this is, like I said, to make the old guard accept you and to make it easier for your customers to build on the cloud and make their customers and their auditors and their compliance regimes and their regulatory agencies happy with them. If you're the security vendors, what you really want is to create the kind of FUD that propelled them making billions of dollars in 1990 and the early 2000s. You want that same FUD to work in the cloud, right? Because you want to ship product. No offense to the gold and silver sponsors of the Amazon Web Services Conference. And if you're the old guard, what you want is these kinds of rules to actually limit how the cloud can be built, how flexible people can be in their architectures. You want things like, I still have to have firewalls, or I still have to buy virtual appliances that say they are firewalls, even if that whole idea doesn't make sense anymore. And so the output we get, the best capture of this conventional wisdom from these very disparate groups is called the Security Guidance for Critical Areas of Focus in Cloud Computing. This is a several hundred page PDF. For those of you taking pictures, the slides will be available. That is by far the more efficient way to get this information. But this is a document you should definitely read, and this figure that they have in there really captures what that entire document is about. And it's about taking these existing compliance models, the ones you see listed here, PCI, HIPAA, GLBA SOX. They also talk about DICAP and ITAR and a couple other things. Mapping those to a security control model, and you look at the security controls. And what do you see in those acronyms? What are some of those acronyms, like NIDS and firewalls and DPI and anti-DDoS boxes, right? All those represent boxes that you used to buy that now you can buy virtual boxes in the cloud. And then you map from the security control model onto the control model, right? I simplified this a little bit here, that you're going from the compliance model, security controls, to the cloud model. So our first problem here is that the compliance model itself is both very slow-moving. It took years and years for PCI Council even to realize that virtualization exists. And now they're only getting around very recently into allowing PCI certifications on top of cloud infrastructures. And for the most part, these compliance regimes are built by non-technologists. Compliance regimes are written by accountants, right? The median person who is sitting and actually writing the rules in a compliance regime or is managing the team to do it is somebody who worked at Deloitte and has an MBA or a CPA and came up through the audit and control side, and then they got more and more technologically savvy as they were exposed to it, but they did not start as engineers or ops people. For the most part, the people who write the compliance controls have never been hands on keyboard, right? The vast majority of them, if you gave them a Catalyst or a ProCurve or a virtual machine to configure, they would not be able to do it, right? That does not make them bad people, right? But that's something we have to keep into account when we think about the documents that they're putting out. Then we have the security controls model, which really these controls, as we saw on the last page, are all controls that were defined in the last age of computing, right? Which apparently ended in 2007 or something like that. But the last age of how we used to build infrastructures. And then we have the cloud model, which is the actual reality you're building on. And my argument, meta argument here today, is that this is the wrong direction. These arrows actually need to go the other direction. We need to take the reality of what we're building and the infrastructure that we're building on, figure out security controls that make sense within that new reality, and then have compliance regimes match what security controls can and can't do, right? And that's what we're going to talk about today, is trying to invert that model a bit. Now, I have no power to make people like GLBA auditors or PCI auditors to accept this reality, but what we're talking about today is real security. Security that actually makes things safe, not the security used for a checkbox so somebody feels happy about you, okay? So if you're here to talk about the checkboxes, have a nice evening. Drinks are on somebody else. If you want to actually talk about security, that's what we're going to talk about now. I apologize, this is, the black in here is not very visible, but this is kind of a very generic Visio diagram of how we used to build infrastructures, right? Here at the top, we've got the internet, we've got an external firewall, we have load balancers and web servers, and a web VLAN. Remember VLANs back in the good old day? And then we have another firewall. That's probably not a separate physical firewall. All these firewalls are probably one device that's with a physical VLAN span into them. We have that other firewall. We have our app servers. and different services. Then we have another firewall to access the database server behind it, right? This is, I used to be in charge of security at a little company called LoudCloud, and this is how we built infrastructures in 2001 for big companies who wanted to be on the internet. And a lot of people have not changed how they do this. So in 1998, how would somebody break into this infrastructure? It's 1998, Nickelback is still cute, cool, and sorry? Injection. Now, most injection attacks hadn't actually been invented in 1998, amazingly enough. Memory corruption bugs, yeah, probably in the web server, right? So if I was trying to break into this, what I'd first do is some kind of port scan against the external infrastructure. I'd figure out what the IP addresses are. I would enumerate all the open services, and I hopefully would find a service that was unpatched. Or if I'm attacking the web app, I'm trying to find a bad CGI bin, remember those, that's running, or I am doing like a script injection attack into a shell script running on top of CGI bin. You know, most of the modern app servers weren't around in 1998, but for the most part I was focusing on the operating system of that first layer. And that's what this infrastructure is designed to protect against, right? Because first I break into the web servers, I take over the web servers, I install a rootkit, I get an outbound SSH port, I have interactive control of the web server, and now I start again. I do an Nmap scan from the inside. I find everything else I have reachability to. I find a unpatched service. I break into that again, and I slowly gnaw my way down until I have the app server and the database server, and I have access, and I'm able to steal money or do bad things, right? This is not how hacking happens anymore. I mean, this kind of stuff happens. If you get hit this way, you really don't know what you're doing. But this is not for competent infrastructures. This is not how people get hacked anymore. These days, applications themselves have tons and tons of flaws that you can manipulate the application to do things you don't want to do. So injection attacks are yelled out, SQL injection and such. You should not have SQL injection in 2012, I'm sorry. It's just something you should not have, but if you do, that's a possibility. But there's a lot of, these days, parameter tampering, bad crypto, basically ways that you can ask the app, do something bad for me, and it'll just do it for you, right? Which is obviously much easier than doing all those different steps. The other way, like say we go back to the Aurora attacks, or the kinds of attacks people are seeing from a state-sponsored perspective, are attacks via the corporate infrastructure. And this isn't just state-sponsored. I have another talk I'm going to be giving at RSA all about the trickle-down effects of cyber warfare. And we are living in the first golden age of cyber warfare right now, for those of you paying attention. And we're not necessarily all the good guys, it turns out, too. This is not a one-way fight. But what we're seeing is that techniques and technologies that people are spending lots of money to invent, lots of government money, are trickling their way down. So kind of the APT attack, the attack from the corporate network against production that the Chinese really refined in like 2005, 2006, is now something that the Romanian gangster in a tracksuit has the ability to do, right? And I think our future trickle down is going to be, right now we've got attacks like Flame, this huge, almost self-aware pre-Skynet virus that was almost certainly written by the NSA and US defense contractors to the tunes of millions of dollars of taxpayer money, has demonstrated that you can have totally autonomous malware that can update itself and download new modules and make attack decisions itself without human intervention. That's the kind of thing that in 2-3 years, those same tracksuit guys are going to be able to buy off of an IRC channel for $1,000, right? And so, so we're talking about kind of today, and where we are today, the APT attack is really hot, right? It's still very hot, it works really well. You find one person at a company that will open up a PDF. These people are called accounts payable people, right? Like, you laugh, but those people's job is all day somebody says, here's an invoice, and they open up a Word document or an Excel spreadsheet or a PDF, like whatever there's a good O-day for that day, their job is to open that document, right? So you find the accounts payable person, you send them that PDF, you take over their machine, you now establish interactive control of that machine, you scan the network, you escalate your privilege on the Active Directory network, usually it's Windows, obviously. There are about a dozen good ways to escalate your privilege to become domain admin. Pretty much all of them work whenever we do an internal pen test of a company. So if you think that you're invulnerable to them, you almost certainly are not. You escalate privilege, you become domain admin, you move horizontally, you take over the CTO's box or a senior admin or the head of ops. From there, you're able to figure out how everything works in the operational side, and now you attack an internal service that gives you the data you want, right? So if you want to steal email, you don't go and you don't go take over a storage array and then pull down terabytes of data and then parse it offline, what you do is you use the little web interface that allows admins to pull email up, right? And that's how APT attacks work, and that's how modern infrastructures are broken into on literally a day-to-day basis. That's the kind of thing that people say, and you probably don't believe me, but right now, as we're talking, there is a critical company in the United States with a DNS-based control channel going to Shanghai, and there's a 17-year-old kid on the other side with a government minder with interactive control and domain admin creds on that box. There's probably actually several companies in this room, represented in this room, or that's true right now. So go check your DNS logs. We can talk about that offline if that's something you're concerned about. So what have we really seen in the cloud then? Now that's, the APT stuff happens all the time. It gets traditional and cloud infrastructures. What are some of the more specific cloud issues? Lost credentials are the biggie. And by lost credentials, I don't mean somebody wrote down on a piece of paper and they lost it. I mean credentials that are either gotten by taking over individual machines and pulling them off an admin box, getting access to a source code repository that has lots of secrets in it, or more likely popping open a single box in the cloud that has credentials on it to access certain services that then allow them to access way more services. We did incident response for a company that was hosted in AWS, where their company was wiped out twice. Disappeared, wiped off the face of the map, all of their RDS volumes deleted, everything in S3 deleted, all their instances turned off. Now, it turns out that Amazon has a very lazy deletion policy, and if you call them up quickly enough, they might be able to recover it. I'm not promising you anything, but in this case, they were able to call them up and get that stuff recovered, and then it got wiped out again. And the reason was that they had lost their credentials the first time, and then they hadn't really truly understood where their credentials were the second time that it got wiped out. That all somebody needed was access to one single machine that had access to SQS or some Amazon service, and that those credentials had been massively over-provisioned with way too much power and could be leveraged to slowly move up until they had access, godlike access to the cloud. So this is the biggie. Overly permissive controls, especially for internal users, giving them too much control is a really bad thing. And bad auditing, almost no company we look at that's either self-hosted or hosted in the cloud can properly recreate what happened. There are very few companies that have the ability to do that. The ones that do are able to recover so much quicker than the companies that can't. So keep those logs, keep them for a long time, and keep them on systems that are not under the same administrative control as your production infrastructure. Infrastructure bugs we see, obviously poor patching is a problem that everybody has. We see it a lot in the cloud though, because what we've seen is, back in the loud cloud days when we wanted to expand somebody's infrastructure, we had to physically go into a data center and rack and stack Sun 450s and stuff, right? Which meant a lot of slipped disks and injuries among employees. These days, anybody in this room is qualified to hit a couple of buttons and have 1,000 instances pop up. But to patch 1,000 instances is actually no easier in AWS than it was in 2001 when we were dealing with Sunboxes, right? And so we see a lot of people not understanding that while it's extremely easy to provision in the cloud and to create in the cloud, it's not that much easier to maintain in the cloud. And you need to plan ahead and have all of your ducks in a row before you start provisioning your infrastructure and building your infrastructure if you want to be able to patch it and keep it up to date. Insecure control plane problems, both in insecure access. Steve Schmidt was up here begging people to use SSL for control plane to Amazon. I'm pretty sure he wasn't doing that just out of the goodness of his heart. Steve had specific situations in mind. I would ask the same thing. And attacks from the corporate network, again, the APT attack. This is how the vast majority, if a company comes to me and says, how would you destroy us? Or how would you steal this money? Or what, I would give you the scenario that starts with an account payable person. Because the corporate infrastructure is this so incredibly messy, nobody has control of it. Generally, the people that are in charge of maintaining it are not as on top of things from a security perspective as the production infrastructure. It is the soft GUI center of any corporation. And then application bugs. Too loose bindings in the cloud. That the cloud really encourages you to loosely bind your application components together to have decompose into tons of services. I think that's a fantastic thing, but you can definitely go overboard and make it too easy for anybody that's within a security group to do anything. And we'll talk specifically about how to design your architecture and not allow that. But we have seen some interesting security bugs about you pop one box, you do a scan, I'm now able to get to all these web services, and if I figure out the REST interface, I can do anything I want. Web and API vulns, we've had these forever, and bad crypto. The most dangerous book for security or for any kind of software engineer is Applied Cryptography by Bruce Schneier. Who owns this book? Yeah, I should have asked first before saying it's so dangerous. The problem with the Applied Cryptography book is it makes any engineer who reads it think that they're qualified to create crypto systems using well-known primitives, right? So you think to yourself, well, I now know, thanks to the power of Bruce, whose tears cure cancer and all that stuff, that Bruce has endowed me with this power to understand SHA-1, I understand AES, therefore I can use SHA-1 and AES and RSA and put them together in a way that makes sense. And it turns out that putting together even of cryptographic primitives, you're not doing any math, you're just putting libraries together, is still really hard to do in a secure way. Get professional help with this if you're going to invent new crypto systems, because we see it all the time where people think this is great, this is great, this is great, and you put it together, and what comes out looks like it's fantastic, and if you look at it for about 30 minutes, there's a padding oracle attack, or there's a reused initialization vector attack, or something that wasn't covered in applied cryptography, and therefore is completely not on the radar of that engineer. Like I said, lost credentials, this is the big, big winner in the cloud, and it's also, honestly, the biggest weakness of AWS versus being self-hosted is the fact that AWS has the ability to have credentials that remotely you can be, it's like you're physically in the data center, right? That's not a criticism, that's how the cloud works, but that's like of all the complaints people have about the cloud, I think that's the most legitimate. These are kind of fantasy issues I'm going to talk about right now, just so people don't ask me, why didn't you mention this? Hypervisor attacks. Hypervisors are fun things to attack, right? They are extremely complicated. They rely on very esoteric bugs and interfaces within the API. If anybody who's worked on hypervisor stuff, if you look into like the Intel errata, from individual steppings of a Xeon chip, they will change how some of the VX instructions work, right? So it is a very moving target if you're trying to write a hypervisor on the Intel platform, because it's just not a very mature technology yet. And there's lots of fun stuff to do here, and because of that, this gets a lot of talk in cloud. There's a lot of Black Hat talks and DEF CON talks and other, CCC and other technical security conferences. Talking about breaking the hypervisor is fun. It's also a great way to get a PhD. It turns out this is a great thing to put into a dissertation and get a PhD. We've never seen this actually used, a hypervisor attack. We've done them ourselves. We have people doing research on GPU stuff. Turns out GPUs were not meant to be multi-user. And they have DMA access and they're bus mastering, so if you get control of the GPU, you can do all kinds of crazy stuff. And so that doesn't stop us from publishing the papers, but realistically, unless you're Northrop Grumman and you're designing the next stealth fighter and you're storing that in EC2 and S3, then you're probably not playing at the level where this makes a lot of sense. Because all the things that have to happen correctly in a row for I start up an instance AWS, I do attack against the hypervisor, I take control of the droplet, the physical box, and then I move through the Amazon network to do bad things. The number of things that have to go right for that to happen without getting caught is pretty long and pretty complex and really unrealistic to be used if somebody had that skill against pretty much anybody in this room, right? Like I said, if you're a defense contractor or something, you're playing a slightly different field. People will do crazy things like break into RSA, subvert the entire secure ID infrastructure just to break into your VPN. So that's like what Lockheed Martin has to deal with, right? Is like, oh, you did an entire 6-month hack of RSA just to attack us. That's fantastic, thank you. But if you're not Lockheed Martin, which I'm guessing most people in the room aren't, then you're probably not playing at the level where hypervisor attacks, they're a fun thing to read about, but don't make this part of your security planning. Covert channel timing attacks are related. These are the kinds of research people have done into, I'm running on a Xen hypervisor box in Amazon next to somebody else's, what kind of information can I get from timing channel attacks by looking at what the processor is doing or the network infrastructure is doing? Usually it's processor stuff. Can I pull secrets out? And people have demonstrated that they can pass secrets through timing attacks from one Amazon instance to another. Again, generally completely useless in the real world, but a fun way to get a PhD. And physical breaches. Steve Schmidt gave a very good talk this morning talking about everything that Amazon does from a security perspective. And he spent a lot of time on the physical stuff, and I completely agree with him in that a cloud computing provider has a huge number of benefits over any corporation that doesn't run only their own data centers. And almost every major corporation is in some kind of shared data center infrastructure, even if you're only sharing like network POPs and stuff like that. In a cloud provider, their ability to run their own data centers with only their own employees and never provide access to anybody means that a physical attack is really unrealistic, again, unless you're playing in that kind of Lockheed Martin spy novel kind of world, which probably none of you are. I mean, you probably think you are, but you really are not. So let's talk about what we're going to do then. So these are the realistic bugs. What can we do to fix them up and prevent some of these attacks? So the obvious one is to use limited accounts in AWS, use IAM. IAM is a pain in the ass, and I'm not going to lie to you. There's a lot of things that could happen to make it easier to use. Just because it's a pain doesn't mean you shouldn't do it, right? You should not be provisioning out those God accounts that you get from the Amazon web interface, the console interface. That should never touch a machine, right? Like a machine in your infrastructure should never have your top-level creds, should never have top-level IAM creds either, right? You should never have a machine have any kind of creds that does more than it has to do. Like I said, keep those creds off of instances. Because what people realize is you take those creds and you burn them into an AMI, or you put them in a config file that automatically gets pushed out via Puppet or Chef. And now what you've created is that every single machine is the entire security infrastructure, right? Like the entire perimeter exists on that machine. And all you have to do is pop one machine in the DMZ that's doing something stupid that somebody forgot about and forgot to patch. You get the creds on that machine. It's real easy to run a grep search to look for things that look like AWS creds. You pull those off, you do a quick web service query, wham bam, I've got tons of power, and then no other protections you put in place really matter. Use key management tools to distribute creds. Don't put them into AMIs. Don't put creds into source code repositories. You can write them on Post-its, right? I've never actually heard of somebody having their creds stolen off of a Post-it. But don't keep them in a place that is hard to change and is that automatically distributed to a lot of laptops. We had an incident response where it was very hard to figure out who did it because the credentials that were used were checked into Git. And so every single technical employee at the company had access to those creds, right? So it's like that kind of whodunit is very, it's like an Agatha Christie novel where every single person is given on their first day coming into the, here's an exactly identical gun, right? So everybody in the room has the exact same gun. Now figure out who did it. This person turned out to be really stupid, so we caught them. But but for the most part, if you're dealing with somebody good, that kind of thing can really make your day bad. Use these limited accounts from day one. We see it's not easy for people to retrofit kind of their operational and production management scheme to now use less powerful accounts once they've started off using God power accounts from the beginning. So from day one, even if you're a small company, you have no customers, you have no auditors, just start to use IAM accounts, create sub-accounts for employees, create sub-accounts for each service, and start that from the beginning because going back and retrofitting is going to be really hard once you're in a model where you have milestones and you're in continuous deployment and you know that rotating those creds is going to have a 50% chance of taking the whole site down, right? Use multi-factor authentication on your top-level accounts. Have multiple top-level accounts. Limit direct access if you're a small to medium-sized company. I'm not going to push any single company here, but any of those management platforms that manage AWS for you that provide like another level of authentication and authorization in front of the Amazon APIs are not a bad choice. And if you're a large company like you're a Netflix, then you can put people on to write the software for yourself, right? But the fewer people you have talking directly to Amazon endpoints, the better it's going to be. Use multiple top-level accounts with shared billing. The whole shared billing thing makes this a lot easier from a management perspective, and we'll talk about in a second, but you really should have different parts of your infrastructure have absolutely no logical connection within the Amazon security scheme, right? If you start them from different top-level accounts, there's no overlap of security groups, there's no overlap of S3 buckets or of IAM accounts, and do that, use multi-factor authentication, put those tokens into a safe somewhere that's physically on-premise, and then use pop holes in security groups and such, and by sharing buckets, you can still do all that, but you start with these very firm lines drawn between the different authentication regimes. Don't allow developers on production, which this is going to piss a lot of people off in here, but if you make it that every developer in your org has access to production boxes like SSH access, or unfettered Puppet or Chef access, then you're done, right? Because eventually you're going to have to fire somebody. That's a really hard thing when people come to us and they say we need to build a secure infrastructure. One of the first things I'm like, okay, what are you going to do when you fire somebody? Oh, we're not going to fire anybody. Everybody here, we're all brothers, right? This is, I get the whole St. Crispin Day speech, right? About how these people are going to fight together and like, okay, great, yeah. Name a startup where there hasn't been one of the first 10 employees fired, right? Nobody can name a single successful company. Like all the ones have failed. If you don't fire somebody in the first 10, then you're going to go out of business, right? So you have to plan for that up front. And one of the things you need to think about is especially for engineering teams or places that teams that might have a lot of turnover. Maybe you're not firing them, but they're leaving. From the beginning, don't give those people production access because taking it back is going to be a lot harder both technically and from an HR perspective because you're like insulting them to their face. Turn over your badge, your gun, and your SSH keys, right? Is the kind of thing that ticks people off. Require all access via Bastion host if you're going to talk directly to machines via SSH. I'm not even going to mention Telnet. Everybody in this room is too smart to use Telnet. But if you're going to SSH directly in the boxes, make people go through a Bastion host. If VPC is a great mechanism to enforce this, otherwise you can do it with security groups where you create a Bastion in the cloud, you log everything that happens on that Bastion host, people have home directories, and that becomes kind of the engineering Bastion where people can have the tools they need local in the shell, and then you can instrument the shell to log every single keystroke and you can turn on process logging and stuff like that, and all that stuff goes offsite using syslog-ng very quickly onto a Splunk server or some other logging system that is in a different authentication domain. Makes it very difficult for a bad guy to grab somebody's account, get in, and then do bad things without getting caught. A proper Bastion host with proper logging will save you a lot of trouble. Log every keystroke, that's what I said. Okay, infrastructure problems. You need continuous internal and external scanning, right? This is actually getting built into the compliance regimes. DIACAP is going to be the first one that's going to kind of push it onto the other ones. But we're entering a new world where it's not going to be enough to say, at this point in time, my auditor said I'm okay. The new world is going to be, my auditor has promised that they are going to continuously enforce the audit and check for new audit findings. And so you're going to be forced into this world if you have any kind of compliance regime where you need to continuously be scanning your infrastructure and able to demonstrate that you're always looking for vulns. You should be doing it anyway, both internal and external. One of the great things about the cloud is that you can't lose machines. There's a very large company that pays us 6 figures every year to find out all of the computers they have on the internet, right? It's one of our favorite projects because it's just like, every year it happens, we reuse the same tools, it's a big chunk of money. It actually turns out to not be very easy. But when you're in a traditional infrastructure in a big multinational, it's not easy to know what your external looks like or your internal network especially. And this is just external, so we can start by doing BGP dumps and looking at the routers and stuff like that. For internal, it's much messier. The great thing about the cloud, you can just do an API call and you can find everything. And so this should be part of your continuous scanning. Obviously, when you set up your scanning, you don't have contiguous IP spaces in the cloud, so you're going to have to do this anyway. Get a scanning engine that will automatically pull the stuff via API, and if it sees a new instance, you're going to scan it. Put those scanning engines for the internal stuff in a security group, and that security group should have pretty much carte blanche access. Now, this gets somewhat controversial because you've also created a single point of failure, so you have to weigh this back and forth. But if you do it correctly, it's probably worth it. I recommend using very, very limited AMIs. Something we like to do is we create chroot, encrypted chroot file systems, pull them down by a user data script. So we'll use a generic AMI, run a user data script that patches it, and then does a pull from S3 of a GPG encrypted tar ball. And that tarball then expands out to a chroot environment, and then we execute whatever services we're going to run within the chroot environment. Chroot's great because it has pretty much no performance overhead, and it doesn't provide like a super firm security barrier, but what it does allow you to do is have the user mode executable environment for that service be very easily patched, right? Because you can very easily then script up, much more easy than pulling down an AMI and pushing it back up and such. It also allows you to have integrity and a checking of the chroot environment and stuff before you push it out, and then that allows you to use something like the Amazon Linux AMIs or the canonical AMIs or something like that. Build your control plane and trust into the AMI. So the first thing any of your instances should do when they're born is they should call home. They should call home using they shouldn't have any hard-coded credentials. They need to have some kind of embryo credential that allows them to get onto Chef or Puppet or something like that, probably authenticated just by the IP address. And then the server side would be authenticated by asymmetric crypto. You can put a public key or a certificate authority on the AMI to verify then the SSL connection. I'm a big fan of running your own certificate authorities just for production uses in the cloud. I could talk for an hour about that, so if you're interested in that, you can talk to me later. Avoid, obviously, burning your SSH keys and anything that are very permanent. Every person needs to have their own SSH key. This is pretty obvious, but we see a lot of shared prod team, dev team, SSH keys that then get burned in the services and such, and so when you finally have to fire somebody, you can't fire somebody and then also have production uptime, right? Deploy corporate controls. So like I said, the APT attack is the hot thing. It's not just governments anymore. This means you need to think hard about what your corporate network looks like to an attacker. Just because you're on a Mac doesn't mean you're magically, okay, everybody get your Mac out and look at how beautiful it is. I'm not going to insult it. It's beautiful and it loves you. And that's great. But you need to tamp down the reality distortion field just a little bit and realize that Macs are not magically, just because they don't get PC viruses doesn't mean they're magically invulnerable to attacks. We did a whole talk at Black Hat 2 years ago saying, what if these companies, instead of running Windows, were running Macs? Would the Chinese been as successful in Aurora? And our answer was yes, that actually corporate Mac networks are more like the NT4 world from an auth perspective. So if you have a managed corporate Mac network, you're actually in worse shape. The best thing to do if you have Macs is not to manage them and have them in individual silos. Don't do any AFP shares. AFP is a disaster from a security perspective. Don't run OS X server. Don't do curb or any of that stuff on the Mac, because that stuff is basically as secure as NT4 was in 1999, 2000. We have a paper published, and you can ask me. I can send you a link if you want to read all about that. But you still, even if you have a bunch of Macs and you're on a DSL line and you have no Active Directory or kind of corporate management, which is a lot of companies, then just think about what you would do. How would you catch one person opening up a bad file, getting their machine taken over, and then their SSH key stolen? Is there a way you detect that? A good thing to start with is a deep packet inspection firewall. I like Palo Alto. I don't own any stock, but I like their firewalls for that. The next step is then to run everything through a proxy, which automatically breaks a lot of malware, and then to have like a deep inspection proxy and stuff like that. Use VPCs to strongly isolate critical services. There's just a whole talk on VPC. I don't have to tell you about it. And then from an application perspective, make security a targeted feature, right? Make security a top-level feature when you're doing your planning and you're in Pivotal Tracker and you're doing your stories. Make the security story part of that, right? Security is not an afterthought. It's not something you staple on. It's not something you do with just a simple checklist. It needs to be part of the design that you think about when you think, what functionally is this product going to do? You have to think about it doing it securely. A lot of people say security and usability are opposites, that they're diametrically opposed. And I have a really smart friend who works at Google now named Chris Palmer, and he always said that security is a necessary but not sufficient part of usability, right? If I go and I do something and it's easy, but in doing so a bad guy does something really bad to me, then that wasn't usable, right? Usability doesn't mean easy. Usability means that something happens like I think it's going to happen, and it's easy to do that, right? And so if I do something and it's easy but it's insecure, it's not really usable. And so don't make that part of your argument. Don't think, oh, if we make it secure, it's not going to be usable, because if your customers are not safe, then it wasn't usable in the first place. It was just easy, right? Create your security engineering group early. Early in your life cycle, think about having developers whose half their job is security, right? Most companies can't afford to have a full-time security person in the first 10, 20 hires, but what you can afford is that one of those engineers is being tasked as you're the person who has to think about security. A big benefit we get as external security consultants is that we haven't sat with you and bought into the groupthink of all the decisions that were made to get to the point of where you are. Right? So often our biggest bugs are found just from interviewing people. We go in and we say, how does this work? How does this work? How does this work? And then we're taking notes furiously, right? And often people will say, oh yeah, well it works this way, but we made that decision for X, Y, and Z. And we're like, well, we don't really care about X, Y, and Z, right? What we care about is that violates all of your security benefits that you thought you got out of this system. And so a good way to head that off is to have somebody whose job and who's empowered to not accept the groupthink. It's really hard to do, but have somebody whose job it is to question, and then don't hammer that person down, just because they're the nail that sticks up. let them question the groupthink and the decisions and be the person who, maybe it's half their job or a quarter of their job, but that's a big part of it. Build a very small set of trusted core components and have your best engineers write them. You should not have 4 different session management mechanisms. You should not have 4 different pieces of code in the same language that takes a username and password and trades it for a cookie, right? You should not have 17 different data access layers to the same database. But we see that all the time where you don't componentize, you productize your system and you say, okay, well this part of the product, this vertical part of the product belongs to Joe. And so Joe writes the session management stuff, Joe writes the cookie handling, Joe writes the input validation, Joe writes the data access layer for his thing. And then Sally writes all of the same things for hers. And instead, the data access layer they use should be written by the data access layer expert who thinks about the security of it once, who prevents SQL injection from happening, who thinks about how access control works on your database schema. And the person who writes the cookie thing should write it once in the session management. That's an important part of this, and that saves you a lot of trouble. It shouldn't be that much harder to change your development mechanisms a little bit. We're going to talk about this a lot, but authentication should not be something that happens on lots of machines. It should be something that happens on a very few, authentication and authorization. And we'll talk about a model where that works. We'll talk about this. Provision internal certs to all instances where possible. Like I said, I'm a big fan of using internal certificate authorities. This is not a product that you have to buy. It is not hard to take OpenSSL and a bunch of scripts and wrap some Python around an OpenSSL and have a certificate authority that now sees a request from an IP address that matches up with an IP address of an instance with a name in the AWS service, generates a cert for it, signs it with a special CA that's just for that purpose, and then gives it to the instance. If you do this early, even if you don't have a use for it, you will eventually find a use, right? You're going to use it for data encryption, you're going to use it for IPsec, you're going to use it for something. And so thinking early about how you're going to provision out a cryptographic identity to every instance that is both tied to its IP and its username. You can use subject alternate names for this. We can talk about X509 some other time if you want to talk in detail, but there's lots of ways you can have multiple names in the cert. Try to get those all into that cert, provisioned out automatically, and you're probably good to go. We talked a little bit about the flaws in the cloud. A good thing to think about is what benefits do we get from the cloud that we wouldn't normally have in our architecture. So one cool thing we get is we get out-of-band trustworthy communication. Now, the trust of that out-of-band communication is actually pretty good. The secrecy of it is not very good, and so you have to take that into account. The user data field is available to anybody who logs into any user on the instance, right? It's not some kind of secret that's passed through the kernel. Anybody can do a web service request to pull it, for example, and stuff. So you have to, when you use these technologies, understand really what they do and how they work under the covers. But there are a bunch of things. So you've got that. You've got trusted network topologies like VPC. You have the ability to have trusted IP addresses on an individual /32 basis assigned to machines. That's a hard thing to do unless you're doing private VLANs with manual typing of IP addresses onto a layer 3 router or layer 3 switch. It's really hard to do that in a physical world, but Amazon's done all that in their hypervisor and their network layer, made it so that there's a /32 provisioned out to every single instance that you can generally trust. And again, generally I mean if you're not Lockheed, right? So, if you're playing in that level, then perhaps we need to think a little bit more about it. But for the people in this room, you can generally trust that. The other thing you should think about is what are the layers of defense that exist for certain violations of the trust model. So let's say your top level AWS account, either an IAM account that's fully privileged, that has no limits on it, or the actual Amazon login to the console is a bad guy has it. What do we have left that is protected from that attacker? For the most part, we've got two things. One, we have the RAM of the instances. So far, there's no web service request you can make to snapshot RAM and pull it out. Now, Amazon has that capability. We've done instant response for them, and they do have the capability, but I know it's a highly protected thing. So it's a very hard thing for them to do internally, and it's not exposed to users at all. You also have the ephemeral per instance storage. Now, bad guys can get all your S3 stuff. They can see the public side of the SSH key pair, but they can't see the private side of the SSH key pair. That being, if you were stupid and put all the private keys into an S3 bucket that the bad guy can read, right? Again, that comes down to how you're going to provision out these creds. But there are a couple of things we can build upon that even in the worst case scenario that my top level accounts have been compromised, that we can limit the damage. Now, obviously that person can make your business disappear. They can delete everything, right? They can do all kinds of damage to the integrity, but you can at least maintain some confidentiality. And so this is one model that you can map that out. You know, we talked about before compliance to controls to reality. This is from reality to controls to compliance, right? And so the reality being that we've got our user data mechanism that allows us to somewhat securely pass information to an instance when it's born. We have the instance memory, which is protected from even the highest level users of the AWS API. And we have trustworthy source IPs. On top of that, we can build a key management service, right? We can drop a user data script that pulls down a chroot environment, or that pulls, you know, an Ubuntu package as an apt-get of a package from a private repository, pulls it down, turns on this key management service. A key management service calls their certificate authority system, saying, I'm so-and-so. That certificate authority system looks at the IP address, matches it up to the API, says, okay, I believe that you're so-and-so, here's your certificate. And now that with that certificate, you can encrypt and envelope all kinds of keys and credentials that get pushed down based upon membership in security groups, for example, or other kinds of things that that key management service can query. And we can have crypto keys, creds to get to services, pre-shared keys. And then on top of that, now we have secure instance-to-instance communication. We have encryption at rest of EBS data, S3 data, things that you put into the message queue, things that you put into RDS. I didn't have time to retrofit this for Amazon Redshift, but once we have those things, we have this reasonably trustworthy path that should not be able to be compromised by an attacker in the worst case scenario. So in the worst case scenario, our bad guy can see all this stuff, but they're not able to see the actual data. They can pull down data from RDS, but the individual records are encrypted, at least the secure ones, with keys that are enveloped from the key management service that are bootstrapped in a way that the bad guy should be very difficult for them to replicate. So a big part of this is if you're in the cloud or not. If you're going to build a services-oriented application that decomposes all the components in different services, you need to build that application so it's very paranoid. And what a paranoid application means that violation of pretty much any of the boxes on your Visio gives a limited amount of benefit to the attacker, right? Obviously, any service that does anything important, if a bad guy has control of that service, they can do something, right? It's unreasonable to think they can do nothing, but what you can do is you can limit the damage. An architecture like this is something we suggested to a company that was doing medical records on AWS, because anybody know what the magic number is in HIPAA? Any med people in here? Anybody ever heard of the magic number? So 500 is the magic number. If there is an event where 500 patients have their personal information released, then it becomes a huge deal under HIPAA. If 499 patients have their information released, it's like, not a big deal, right? And this is for lawsuits and compliance and a bunch of disclosure laws, right? And so what this company wanted was to be able, into almost any circumstance, to be able for us to write an expert witness report that says we can prove that 499 or fewer patients had their data exposed, right? And this is the way you can do something like this. This is an expandable process. So we have, our ELB up front. We've got our app servers. These dotted lines are security groups. The different colors are different authentication regimes, right? So our authentication service up top is running as a totally different top-level Amazon account. The logging system's running as its own Amazon account. And the request comes into ELB. It gets dished out to our stateless application servers. These are stateless, clearly. It gets a username and password or a two-factor auth token or something like that. It trades it into the authentication service. The trading of a credential to authenticating and authorizing a user is, again, something that is not super common, is not computationally intensive, and can exist in a very small part of your infrastructure. You don't need every single app server to be able to query a database, look up the password hash, compare it, and then say this person's authorized. You only need a very small part of your infrastructure. A small part that doesn't do a lot, that has highly audited code, that is maybe integrity monitored in a way that is not reasonable. You have tripwire turned up all the way. These machines are almost never touched. Nobody has access to them. I turn in my two-factor auth token or my password. In return, I get a secure token, which we'll talk about in a second, that represents the authorization that user has on the system. This token can either be statefully stored here in the app server, or better yet, can be encrypted and sent back, serialized, encrypted, and sent back as a cookie, so that now every subsequent request is tagged with a cookie that then, when decrypted, is the auth token. And now every time I call any of these backend services from my decomposed infrastructure, I have that auth token, and each service is able to verify, yes, this app server is, Bob logged into this app server. The app server has been authorized by Bob to make this request on his behalf. And every time any of this happens, we throw it into the logging system down a one-way tunnel. Syslogin G UDP packets are probably good enough. There is a little bit of UDP loss in EC2 sometimes in high load situations. So some of these things you might want to do over TCP, or you might want to use a Splunk or something else that has agents that then does buffering and reliable delivery. But whatever you do, it's going into a system that's under a different authentication regime and that's not accessible to almost anybody, or if it is, it's only in a read-only situation. And what that token looks like that you went to the auth service and got is you have identity, right? You have some kind of primary key that identifies this person, might be their email address or something, might be a GUID that you generate on the provisioning of an account. We have context, the kind of context you need to rewrite the page to make it easy, like the org ID, the username, all that kind of stuff. The kind of things you keep in session state in memory, usually. We have permissions that are set, like group membership. Maybe this person's an admin or not within their organization. You could also do this with a bit mask. And then we have crypto keys that allow me to de-envelope encrypted messages elsewhere in the system. I'll talk about that in a second. And this whole thing is signed, not encrypted, but signed with a public key, private key that belongs to the auth server that can now be verified asymmetrically by every single service. And if you're worried about size, I recommend ECC. It's not as patent encumbered as you think. And with ECC, you can actually make the signature reasonably small. This whole packet can fit into 500, 600, 700 bytes. People complain about the size of this kind of stuff, and it's like, I just looked at your code and you're doing a 47K REST request, to find out somebody's email address or something, right? So don't complain to me about the size of the security token. It's something that can be made pretty small, especially if you use something like protocol buffers or some kind of really much, a better serialization scheme than XML or JSON. And for the per record stuff, so we now have this token, right? So I'm the backend service. The web server said Bob wants to read this data. Here's Bob's token. That token has in it a symmetric key that belongs to Bob. And so for every data record, we take, cryptotext equals the encryption of the plain text with the key sub s. K sub s is a per record symmetric key. That symmetric key is then enveloped by all the people who have access with it and then appended onto the record, right? You can either do this as a different part of the data store or actually in the record itself. And so for our most secure, our most concerning records, it's enveloped with a key that can only come from the auth server. And in this case, the user himself is allowed to access his record. He's part of a group that can access it within the application. Maybe there are several services. You have a data warehousing service that has to be able to access this record. It has its own key, and that's enveloped automatically when the record's created. And then we have a master backup key, a symmetric key. An asymmetric key. And these could be either symmetric or asymmetric. Asymmetric makes the security principles a lot easier to understand, but it makes it a lot slower. You can do it with symmetric, but it's a lot harder, as the Curb people have found. And with a master key that's then used kind of as backup in case we have a catastrophic situation, you have to do a database recovery or something like that. That's the kind of key that can then be requested by a high-level admin or is in the CTO's hands. As a result, there is not a single box here except maybe the authentication service itself. Well, I guess not even the authentication service. There's not a single box that you can pop and do really bad things, right? You have to pop one of these services, and you have to have control of the authentication service. And like I said, that auth service is something that is highly monitored and controlled, and perhaps even has, if you have security requirements that don't allow you to be in the cloud, then you put the auth service with all the keys in self-hosted infrastructure. Obviously, you get rid of all the reliability benefits because it's a critical part of the service, but that allows you maybe a transition into the cloud by moving it off-site first. So that's just one architecture, but that's one way that you can take the things you get out of the cloud and turn it into lots of protections that it would be very difficult to get in self-hosted. So our conclusions are, I don't recommend trusting the conventional wisdom on the cloud. Like I said, the conventional wisdom is useful if you want to reference something to make auditors happy, not so useful for actually making your system secure. You should consider the realistic threats to your org. Don't spend all your time reading papers about hypervisor attacks. That's not going to make you any safer. Spend that time thinking about who has creds in your system and how they're given out and how they're revoked And how do you fire people, right? If you're a small company and you haven't done it yet, you need to think through, is there anybody in the org who can't be fired? Now, you might make it yourself that you can't be fired,